And the last word of ancient cosmology from the Greeks was the Ptolemaic model, put together by Claudius Ptolemy in the early 2nd century AD, about 1900 years ago. Now, it's easy enough to explain with that model I showed you a little bit ago. The thing spins every day, and that would explain why the sun rises, why the stars rise, and why they set, why the planets and the moon do as well. You see, the stars remain fixed with respect to each other as they spin around us each day and each year. By the way, these stars shift from year to year, throughout the year, because you get on different sides of the sun as you orbit around, and in the geocentric model you would have the sun moving through the stars. So for instance, in the northern hemisphere right now, Orion is a winter constellation and Scorpius is a summer constellation. Now it's going to be switched, of course, in the southern hemispheres because the sun appears to move through the stars, again, I think due to our orbital motion around the sun every year. However, there were 6 other bodies that moved through the stars. The sun moved through the stars once a year. The moon moved through the stars once a month. That's the definition of the month. And that's due to the orbital motion of the moon around the Earth, I believe. But then you have the 5 naked-eye planets, Mercury, Venus, Mars, Jupiter, and Saturn. And they're look like bright stars. In fact, they were called wandering stars, which we get the word like planetes aster, which means wandering stars. We get the word planet from that Greek word. Now, they follow a complicated motion. The sun and the moon both move west to east with respect to the stars, and so do the planets. We call that direct or prograde motion. But occasionally, the planets will seem to reverse and go the other direction. So you got the planets up here in the sky. They're going west to east with respect to the stars, but then occasionally they stop and go backwards, and then they move forward again. While they're going backwards, east to west with respect to the stars, we call that retrograde motion or indirect motion. How do you explain that? You just can't have them turning around and changing their minds. So they came up with this clever idea. Ptolemy probably didn't create this idea, but he did codify it and set up a good model. He wrote about it, which made his book very popular throughout late antiquity and throughout the Middle Ages. The Ptolemaic model, I think, was the most successful theory in the history of all of science, if you measure it in terms of longevity, because it was written up in the early 2nd century AD, and it was accepted by and large until this early 17th century. So we've got 1,500 years of this model being accepted. That's a very long time. No model we have today, no theory we have today can match that in terms of longevity, not by a long shot. And the strength of the model is that it could be continually modified. You see, occasionally, after observing the planets for a few centuries, they notice slight deviations. And there already was a second epicycle thrown in for each of the planets. You can see the planets bob up and down a little bit. That's caused by the different inclinations of the planes of the orbits. But so what Ptolemy did is he put in a second epicycle. You got the main epicycle going like this, and then you get another epicycle perpendicular to it, so the planet bobs up and down and makes an S sort of pattern or a loop sort of pattern, and it matches the data really well. So now you have like 11 epicycles for all the planets and the sun and the moon. Well, after a few centuries, slight discrepancies, so the way you fix that is to put in a third epicycle. And then more discrepancies, a fourth epicycle, and then a fifth epicycle, and so forth. It got to be to the point by the time you get to like 1500, the year 1500, some systems of modifications of the Ptolemaic model had 100 or more epicycles on epicycles on epicycles. It was a mess. In fact, in the late Middle Ages, transition to modern times, there was a Spanish prince that was being tutored in the Ptolemaic model, and when the tutor got finished, he said, you know, if I would have been present at the creation, I could have given the creator a few suggestions. He realized it was way too complicated, and usually there's a principle called Occam's razor, tells you if confronted with two explanations, the one that's simpler probably is the correct one. So that was the strength of the model, that it could be continually modified, but it was also the weakness. You could continually modify. You see, if a theory can be modified to explain any new problem, then it really isn't a very good scientific theory at all. Sir Karl Popper wrote extensively about falsifiability in science, that at least at some levels, you must be able to disprove a theory. Even if you don't, it doesn't matter, you ought to be able to do it. But you see, the Ptolemaic model could not be disproved. All you had to do was add more epicycles to explain away the problem. What ultimately did it in was the complexity itself, because people realized there's got to be a simpler way to explain this, and Galileo was one of those people who was pioneering that. And probably most of what you heard about the Galileo affair isn't true. They try to say it's religion sticking its nose where it shouldn't be. In reality, it was far more complicated. It was basically new science challenging the old science. So there's an interesting story to tell there, but what you probably learned in school probably isn't correct. Now you may wonder what that has to do with modern cosmology. I'll come back to that a little later. But modern cosmology, when you mention that, the name Edwin Hubble comes up very quickly. And here's a photograph of Edwin Hubble at the eyepiece of the 100-inch telescope that he used over top, that's 2.5-meter telescope over top of the Los Angeles basin. And he made three great contributions to cosmology. His first one was in 1924. He proved that other galaxies exist. Up to that point, the dominant theory for quite a while was that the Milky Way galaxy, our galaxy, was the only galaxy in existence. But in 1924, in one fell swoop, he suddenly made everyone realize that there were millions of other galaxies out there. And so the universe suddenly got much larger than it ever had been. In 1929, he's credited with discovering that the universe is expanding. Now, what about this expanding universe? The way many textbooks describe Hubble's work on the expanding universe, they make it sound like he just stumbled across it by accident. That wasn't what was going on at all. He knew exactly what he was looking for. And the story goes back about a decade before he made this big discovery. You see, in 1915, Albert Einstein had published his general theory of relativity. And then the following year, he applied it to the entire universe. And if you do this general solution to the universe, which was done in 1922 by Alexander Friedmann, Einstein actually kind of missed the general solution, but Friedmann didn't. He proved that under general relativity, there were two possibilities. The universe could either be expanding or it could be contracting under its own gravity, or it could be expanding. It couldn't be in between. The only way it could be in between is if you had some sort of force that was constraining it there. And what Hubble did is he measured the distances of a number of galaxies, and then he measured their redshifts. Now, what is redshift? Well, the light of a galaxy can be shifted towards longer or shorter wavelengths. The longer wavelengths is towards the red end of the spectrum. The shorter wavelengths will be towards the blue end of the spectrum. And it's similar to, not identical, but similar to what we call the Doppler effect. And this happens in sound all the time. If you're say at a railroad crossing and a passenger train comes by and it blows its horn, you may notice if it holds its horn as it passes by you that the pitch is higher as it's approaching you, it's lower as it goes away, and you hear this pitch change like bow goes by. If a horn of a car, a truck comes the other direction, same thing happens. It's this bow as it goes past, because as it's approaching you, the sound waves are crammed together, making a higher frequency, so it's a higher pitch, and wavelengths are shorter. But when it moves away from you, those waves are stretched out like this, longer wavelength, lower frequency, lower pitch. Well, the similar sort of thing happens with light, except now when you go to higher frequencies, shorter wavelengths, it's not pitch, it's a bluer color. When it goes the other direction, longer wavelengths. When it's moving away from you, it's going towards the red end of the spectrum. And galaxies are all in the red direction. A man named Vesto Slipher, 15 years before Hubble did his work, had shown that. So very few, he knew, number one, that galaxies were redshifted. He also knew about the two possibilities from Friedmann, either contracting or expanding. The redshifts already seen by Slipher were confirmation of the expansion and not the contraction. So all he did is he put these together. And he was one of the few people who understood this connection. and it also had telescope time on the largest telescope in the world, which at the time was the only place you could do this. So he measured redshifts, and he measured distances, and he put those together into a plot, and that gives us the Hubble relation. And the Hubble relation is merely a plot of redshift versus distance. Redshift on the vertical axis and distance on the horizontal axis. Let me show you a publication of his from 1929. He published this, and this is an exact duplicate of what he had. He has velocity on the vertical axis. The higher up you go, the faster it's moving away from us. And then down here we have distance, 1 million parsecs, 2 million parsecs. And you'll see with your eye, forget about the lines drawn through the data, you got dots and circles. And you can see that the galaxies that are closest to us have the smallest distance, have this lowest velocity. As you increase the distance, the velocity or the redshift increases. You can, even without the lines, you can see that trend in the data. And that has been improved upon over the past 100 years. Instead of having a handful of data points, we now have millions of data points, and it's a strong correlation. Distance and redshift for distant galaxies is indeed correlated. Okay, what implications does this have then for the past in the universe? What about the future of the universe? Remember, from the ancient Greeks, everybody thought the universe was eternal. So therefore, the universe must have been expanding eternally would be the idea. And you would think that as it expanded, the universe would get less and less and less dense. That's what actually happens when you expand things, right? But if the universe is eternal, it's had an infinite amount of time to get expanded, so why do we even see galaxies at all? They should be so far apart we shouldn't see them anymore, yet there they are. How do you explain that? It's called the continuous creation model sometimes because matter is continually being created to maintain a constant density. This way, you can have an expanding universe and at the same time have an eternal universe. And this was widely accepted well into the 1960s. But not everybody agreed with that. Some of them thought, we think matter conservation is more important. One of these was Georges Lemaitre, photographed right here. He was a theoretical physicist. If you notice he has this clerical collar on, you're absolutely correct. He was also a Belgian priest, Roman Catholic priest. After all those Roman Catholic universities need faculty, don't they? And why not have priests do it? So he's a theoretical physicist. And about the time that Hubble was doing his work, he published what he called the primeval egg, primeval atom, or the cosmic egg. He believed that the universe began in a very hot, dense state, expanding, and as it expanded, it became less and less and less dense. This is a clear break from what had happened over the previous 2,000 years. He's now suggesting that the universe is not eternal, but had a beginning. And this is a precursor to the Big Bang, kind of naive, published again around 1930 or thereabouts. The Big Bang models we now know, it came about 2 decades later, a little different form, but this is the precursor of it. So what is the Big Bang model? It's the belief that the universe began in a very high density, very high temperature state. It came into existence expanding, and as it expanded, it had to cool, became more rarefied, and so eventually galaxies and stars, planets and people came about, and we have the universe we see today. Now, this met a lot of early rejection. Part of the problem was, for 2,000 years, you're thinking the universe is eternal. It's really quite difficult to imagine then that the universe is not eternal. It had a beginning in the finite past. But even worse than that is the fact that to many people that suggested there must be a creator. If the universe came into existence, that would seem to violate the first law of thermodynamics as properly understood. And so you need a supernatural event to get around, a miracle to get around that, which screams creator. So many people were motivated, not so much by the inertia of believing in an eternal universe for 2 millennia, but also by the fact that this drags you back to theism, and they didn't want to do that. However, this all changed in 1965 with the discovery of the cosmic microwave background, or CMB for short. Well, what is that? Well, I'm glad you asked. We have here a plot made from data collected a number of years ago. It's in the microwave part of the spectrum, the wavelengths on a logarithmic scale here on the bottom. And over here we have brightness measured in the units you can see there. And you have a number of data points, the round dots, the little X's, the little green X's, all of those are data points on this. And it's been fitted to a 2.726 Kelvin black body curve. That's the dotted line. And if you look at that, you should be impressed with the fit. The fit between the dotted line and the data is really, really good. Now, what had happened is in 1948, there was a paper published that's now considered the first modern, more correct theory of the Big Bang. And in that paper, they predicted that there was a time in the past when the universe was very hot, and the universe was opaque, and you get this black body spectrum given off. Black body is a perfect ideal absorber and emitter of radiation. That's why we call it a black body, because dark objects tend to absorb and emit better than light ones do. And they said when the universe became transparent, the matter and energy became decoupled, and now before that, matter and energy, the light were tied together. Light couldn't travel very far without being reabsorbed very quickly. So when it became transparent, the light now is unencumbered and could travel and shoot away, but those photons of light are now redshifted because the universe has expanded so much since that period of time. So instead of being a 3,000 black body curve, it's around 3 Kelvin. And so began the modern cosmology. You see, when Penzias and Wilson, Arno Penzias and Robert Wilson, discovered the CMB in 1965, it matched the prediction made 17 years before, and it didn't match the prediction of the steady state model. In fact, the steady state model cannot account for there being this black body curve, the CMB, out there. So for the past half century or more, it's been about the only cosmology around. There are a few holdouts out there, but almost everybody believes the Big Bang. That's the modern story of how the universe came to be. And many Christians began to follow in that too. They said, look, we can see Genesis chapter 1 in there. They would want to read the first verse of Genesis, something like this. In the beginning, with a Big Bang, God created the heavens and the earth. Well, they then move on to use this as a very evangelistic tool. They say, look, we now know the universe had a beginning. It wasn't eternal, so there has to be a creator, and let me introduce you to that creator, the God of the Bible. That's a very persuasive argument, isn't it? But I have two questions for you. Number one, is the Big Bang model true? Is it the correct model? And number two, is it biblical? If the answer to either one or both of those questions is no, then this is not an evangelistic tool at all. It's really, you're going to be basing your evangelism upon a falsehood. So there are problems with the CMB, the big thing that supposedly proves the Big Bang. That's the big proof, the one big proof they have with the Big Bang. For instance, they tell us that we have structure in the universe, we have galaxies and so forth, but the early universe had to be very smooth, but not totally smooth. What you needed were some slight density enhancements. Some parts of the universe were a little more dense than things around them. They acted as gravitational seeds to pull more matter towards them, and that would give rise to structures that give us galaxies, stars, planets, and eventually people. So we're sitting here looking out at the universe and marveling over what we see. But you have to be very careful, because you see, if you make it too clumpy, all the matter gets sucked up into black holes. We don't get galaxies, stars, planets, and people, and we're not here. On the other hand, if it's not clumpy enough, it's too uniform, then it keeps expanding uniformly, and we never get galaxies, we never get stars, we never get planets, we never get people, and again, we're not here. It's a very delicate balance that you have there. So they said, look, if you have these gravitational seeds in the very early universe, it will show up in slight variations in temperature in the cosmic microwave background. There'll be slightly cooler regions and slightly warmer regions as a result of this amount of clumping that takes place. And back in the 1970s, they were able to predict how much clumping there ought to exist in the universe and how much the temperature fluctuations, as you look in different places in the sky, in that CMB ought to be. And it turns out to be like 1 part in 10,000. That is, the temperature is 3 Kelvin, but it varied by 0.0003 Kelvin from spot to spot. Not a big variation, but by the 1980s, we had instrumentation that would do that. So in 1989, NASA launched the COBE experiment, Cosmic Background Explorer, with the 2-year mission, not the 5-year mission, but the 2-year mission to map the entire CMB looking for those fluctuations. And it was designed specifically to detect the predicted fluctuations at 1 part in 10,000. So they sent the mission up after 2 years. What did they find? They found out that the CMB was perfectly smooth, no temperature fluctuations. What happened to the prediction? It failed! When your prediction fails, it's supposed to disprove your model, at least some aspect of the model. Well, they went to work and they started applying statistical packages, and they found hints of evidence that there were fluctuations an order of magnitude lower. Instead of being 1 part in 10,000, it was 1 part in 100,000. Now, usually when you're off by a factor of 10, you're just way off. Would you cross a bridge over a river if you knew the engineer that designed it was off by a factor of 10 in figuring it? Would you get aboard an airplane that was off in a factor of 10 its ability to fly? I don't think so. And I have to wonder about this as well. Well, what was the fix? How did they fix this problem? Well, what they did is they took the data they had, which showed fluctuations of 1 part in 100,000, and they adjusted the model to fit the data. Now, bad enough, they turned around after the fact and tried to claim that, I've seen claims in print about this, I see them quite frequently, they say the data beautifully matched the model predictions. Of course it did, after they had the data, but that's not a test for anything. They needed to test the prediction, and that was not the original prediction. I have a better memory than that. I know that they were off by a factor of 10, but you don't hear about that much anymore because they've changed the model to change the data, to fit the data now. And by the way, here's the map from COBE showing what the sky looks like. Some people have a hard time visualizing what this is. Have you ever seen a map of the whole Earth surface shown like this? You've got the poles up at the top and at the bottom, and you've got the equator running across the middle. That's what we have here. This is the whole sky, but instead of looking down on like we would on the Earth, we're looking up at the sky. So we got the poles and the equator, and the modeled appearance is due to those differences in temperature. The yellow and the red are the warmer than average, and the blues, the light and dark blues, are the sign of the below average. I guess the greens are kind of in between, but you've got this color coded, so you get this modeled appearance, and that's basically what it would look like. Fluctuations of 1 part in 100,000. I'm impressed. That's really, really, really faint. We'll come back to that. Now, there are 2 other problems for the Big Bang. One's called the horizon problem. And remember I talked about how accurate the 2 temperatures were. If you forget the 1 part in 100,000 fluctuations, let's say I'll look over in this direction at what I'll call point A, and you get this radiation coming from that point A just now getting to me, and that takes 13.8 billion years to get here, because that's how far away it is in light years. Now, I'm also going to look over here to point B, also 13.8 billion light years away, and light is just now reaching me from here. Microwave gets right here to where I am now at point C, halfway between A and B. Now, if the light from A is just now getting to me, and the light from B is just now getting to me, is there any way that light from A has gotten to B and B from A? And the obvious answer is no. It doesn't depend on which direction you go, this way, any pair of opposite directions like this. It's impossible for those things to have been what we call thermal contact. Go back to grade school science. You learned about 3 ways to transport heat. You can do it by conduction, convection, or radiation. As it turns out, radiation in this case is the most effective way to do this. In order for these things to have the same temperature, they've got to come to thermal equilibrium, we say. That's a fancy word for that term for that. But in order for them to be at the thermal equilibrium, that is the same temperature, you have to have radiation getting from this point to that point, but they never have. So why is the universe all the same temperature? And we call this the horizon problem. Now, many times we recent creationists who believe in 6,000-year-old creation, they say, well, how can you see distant things like the Andromeda Galaxy 2 million light years away from you? That's impossible. That's called the light travel time problem. folks, I've just shared with you, the Big Bang has a light travel time problem. We call it the horizon problem. We're not the only ones with a light travel time problem. If they're allowed to explain theirs, then we should be allowed to explain ours. It's the same thing, folks. All right, so the C and B has the same temperature in every direction, even though they've not been in thermal equilibrium. And because they've never been in thermal equilibrium to come to the same temperature. But there's also the flatness problem. What is the flatness problem? Well, it has to do with the geometry of the universe, but you can express it several different ways. The one way I like to do it is to talk about this parameter we call omega. And omega is the ratio of the gravitational potential energy of the universe to its kinetic energy. Kinetic energy is energy of motion. Things that are moving, and galaxies moving through space have energy, so they have kinetic energy, so they have kinetic energy here. But gravitational potential energy is due to the gravitational effects of all things in the universe. As the universe expands, both of these quantities change. They change in different directions, which means that the value of omega can't remain constant. And if the value of omega initially at the beginning of the Big Bang is greater than 1, by even a tiny, tiny, tiny amount, it will increase and increase and depart from 1 very quickly, especially after 13, 14 billion years. But if it's less than 1, it will go towards 0 and will get identically equal to 0 over billions of years once again. So the point is, after 13.8 billion years of cosmic evolution, the value of omega ought not to be anywhere close to 1. It ought to be very close to 0, like 0 to like 20 or 30 decimal points. And it should be very, very large number. Again, nowhere near 1, but yet repeated measurements of it over the years have indicated that it's very, very, very close to 1, and they suspect it may be identically equal to 1. How can that be? Again, two huge problems, the horizon problem and the flatness problem, well recognized apparently in the 70s and into the 80s. Well, speaking of the 80s, in the 1980s, there was a great solution put forth called cosmic inflation. What is cosmic inflation? Well, the Big Bang happens, and while the universe is very, very tiny, it comes in thermal equilibrium with itself. The universe is so small that the radiation can be exchanged, so the universe comes to all one temperature. But then the universe suddenly begins to expand very rapidly, far, far faster than the speed of light. When did this happen? Something like 10 to the minus 34 to minus 10 to the 32 seconds after the Big Bang. When I say 10 to the minus 34 seconds, that's point followed by 33 zeros and a 1. And 10 to the minus 32 is point followed by 31 zeros and then a 1. Very brief, far faster than the speed of light. And this, folks, would solve not only the horizon problem, but also the flatness problem. That's great, isn't it? But you know what? Science doesn't rely upon just trying to explain away problems. It relies upon evidence. What is the evidence for inflation having happened in the distant past? There is none. There's not a bit of evidence. We would say then that this is an ad hoc explanation. Cosmic inflation is, and ad hoc is Latin for we're making this up as we go along. Well, no, it's for the good. But anyway, just making it up as we go along is a better way of saying it. And notice what's happened here. Cosmologists today, astronomers, physicists, they all seem to, most I should say, overwhelmingly majority of them, accept that inflation happened. But there's no evidence, and so it's not falsifiable either. It must have happened because they say, if you ask them, press them on this no evidence for it, they'll say, well, we're here, aren't we? If we weren't here, we wouldn't be having this conversation, so it must have happened because there was a Big Bang. You see what they're doing is they're asserting the Big Bang to prove the Big Bang happened through this method here. There are other problems as well. You know, if you study electricity and magnetism, there are no monopoles. What happens, if you take a bar magnet, it's got a north and a south. If you cut it in half, you'll have two magnets, a north and a south. No matter how many times you cut the magnet, you'll still have a north and a south. It's a dipole, we say. It has two poles there. However, according to particle physics, there should have been at least a few magnetic monopoles in the universe. They like to say, well, the density of monopoles is, and they've looked for these, by the way, they've looked for monopoles for decades and haven't found any. The explanation, of course, is that inflation took place, and when it did, it yanked all the monopoles away from us, and we just don't happen to live in a universe, in a portion of the universe where there are any magnetic monopoles to find. Okay, maybe if you want to put all your eggs in that inflation basket, but what about this? There's an asymmetry between matter and antimatter. I'm sure you've heard about matter or antimatter on, say, Star Trek and other shows. They power the Enterprise in science fiction, where they power the Enterprise and other spacecraft with antimatter. You know, when antimatter and matter get together, they annihilate with a tremendous amount of energy release. It's the most efficient energy source possible. And you might think because you hear about it in science fiction, it's science fiction. It's not. Antimatter is real. You have to conjugate the wave function of matter particles like electrons and protons. When you do that, you get an identical particle but with kind of mirrored properties like opposite charge. And when they do meet, they annihilate each other. And in experiments, we've been able to create antimatter and detect it. It doesn't last very long, but it's there. So antimatter is real, but we don't see any antimatter normally in the universe because our universe is dominated by matter and not by antimatter. This is where it gets interesting. The theories of the Big Bang and particle physics tell us that when the universe came into existence, there should have been symmetry between the two. Yet, there isn't. And they've tried to explain that away, all unsuccessfully. Why do we live in a matter-dominated universe? It's impossible in the Big Bang model for that to happen. There's a thing called the axis of evil in the cosmic microwave background. Remember that thing that proved the Big Bang model to most people's satisfaction? Well, the axis of evil is this circle going around the sky, and the upper half of that is slightly warmer than the lower half of that. This is really big. Half the universe is a little warmer than the other half. That's really strange, but it gets stranger still. That axis of evil the division between those two halves is actually coincident with the plane of the Earth's orbit around the sun. Now, it's weird that you have this axis of evil in the first place, but why is it aligned with such a local thing like the Earth's orbit around the sun? That's very strange. There's a big cold spot as well, and the big cold spot is this region that's very cold temperatures. Well, relatively speaking, it's a large feature that's far too big to be accounted for in the Big Bang. Remember the little tiny modeled temperature differences we saw earlier in the CMB? Well, this large cold spot is too big to be accounted. They've got to be small, and it can't be there. And here's another map. This is a different version, I believe, but the great cold spot is down over here in the lower right down there. And it's just a very cooler region that's too large to be accounted for by the Big Bang model today. So I've given you several things wrong with the Big Bang model. Some of it's actually tied up directly with the CMB, which is supposed to be the big proof of the Big Bang model. So I've noticed in my lifetime, I've been paying attention to this for a half century or so. So what have I noted over the years? We have all these changes taking place in the model. For instance, the expansion rate has changed. For much of my life, the expansion rate was 50 kilometers per second per megaparsec. Now it's about 70 kilometers per second per megaparsec, and the error bars on those don't overlap. When they changed that back in the early 1990s, changed the value of the Hubble constant, the rate of expansion of the universe. It also changed the age. They were telling me for the first half of my life that the universe was 16 to 18 billion years old. Then they said it was 13.7, but then later on they upped it to 13.8. And by the way, that 13.8 billion years is within plus or minus like a percent or so. But that doesn't overlap with what they told us back then. So it's completely different from what we had before. Dark matter was introduced really in the 1990s into cosmology. I happen to believe dark matter is real. It's not a rescuing device. It really is a real effect. But dark matter would account for 90% of the universe. If you have a cosmological model where you leave 90% of the matter of the universe out, and you believe that gravity is a dominant force, and they do believe that in cosmology, then if you leave out 90% of the matter in the universe that is responsible for gravity, your model can't be very good, can it? Yet they left it out for years. Now they include it, not because they want to necessarily, but because they have to, because they've come to realize that much of the universe is in dark matter. Also around 1998 or 99, they brought back what's called the cosmological constant, something that Einstein introduced in 1916, and 15 years later said it was the biggest blunder ever made, but now it's back. They call it dark energy instead. And what it does is it causes the universe to expand more rapidly all the time. So we can do a comparison of, say, 40 or 50 years ago, what the Big Bang model was like. Back 40 or 50 years ago, there was a different expansion rate. There was no inflation yet. There was no dark matter. There was no dark energy. There was no string theory, which I haven't talked about. In short, the model back then was totally different from the model today. Yet back then, they had complete confidence in the theory, just as today they have complete confidence in the theory. Now, I'm a student of the history of science, and I don't know what the Big Bang will be like in 40 or 50 years from now, but I can make two predictions. One prediction is that the Big Bang model will be very different in 40 or 50 years than it is today, and the other prediction is that they will have complete confidence in that theory as well. Well, doesn't this start looking like epicycles? Remember epicycles? The epicycles of the Ptolemaic model, the most successful theory in the history of science in terms of longevity. 1,500 years, and the strength was they could change it at will to explain any problems that came up, but ultimately it was the weakness, because you could change it to explain any difficulties that came up. You see, it was not falsifiable, and I think Big Bang model has become that sort of theory. It can't be falsified. It's being continually changed, and I think if the history of science is any lesson, a teacher to us, it tells us that eventually the Big Bang model will go away. Well, what about the origin of the universe? If the Big Bang happened, I said it suggests a creator. And a lot of Christians like to glom onto that and say, pastors and theologians and some scientists say, wow, this proves that the Bible is true after all. So some people see God in all of this, but not everybody. There are a lot of scientists that say, no, there's no God. We have what's called a quantum fluctuation that takes place. With quantum fluctuations, which have been invoked to explain certain things we see, like even in modern electronics, the idea is that you can have small violations of the conservation of energy, but only for a short length of time. As long as the violation is not very large, and as long as it doesn't last very long, you can have slight variations and violations of conservation of energy, but they have to go out of existence from time to time. And they say, well, wait a minute, what if the universe happens to have zero total energy? Then if that happens, then the universe could come into existence in a way that's not inconsistent with the first law of thermodynamics, because there's zero energy, and it could last forever. That is, it can always be there. By the way, is the total energy of the universe equal to zero? Well, no one's able to demonstrate that. They come up with clever ways to make it happen, but there's no real data to prove that contention. Again, you're getting something for nothing. The universe doesn't exist, and it doesn't violate the first law of thermodynamics. So there are two great quotes out there by some theoreticians on this about how quantum fluctuations can explain the existence of the universe, how it came about. One person said the universe is the ultimate free lunch. You've heard that free lunches don't exist? They do, apparently. And then, I love this even better. One person said, the universe is just one of those things that happens from time to time. Now, both of these are humorous, but they're not a joke. This is reflecting the true beliefs of many, many people today. They are willing to stake their eternal destiny upon this very speculative idea that somehow the universe came into existence through these ways. So I think there's a real problem here. The first question was, is the Big Bang true? I don't think it is. You got some problems there. But then another question is it biblical? And I don't think it is. You see, the Big Bang happened 13.8 billion years ago. Yet Exodus 20:11 says the heavens and the earth were made, and all that is in them was made in 6 days, and then God rested. And we have genealogies in the Bible that tell us that it was about 6,000 years ago. In the Big Bang happens 13.8 billion years ago. Stars start forming within a few hundred million years, but the solar system and the earth don't come around for another 9 billion years. How many stars existed before the sun and the earth did? Billions and trillions and quadrillions of stars. Yet Genesis 1:14-19 says that God created the stars on day 4, after the earth. Furthermore, the Big Bang is an ongoing process. It happened in the past, but the Big Bang is still unfolding. Yet Genesis 2, 1 through 3 says creation was finished and complete after the 6 days. Those are just some of the contradictions with the Bible we find in these evolutionary ideas. But a big question is, where do you place the time? I've gone on record saying that I believe in 6,000 years creation, but I'm open to the possibility that it could be longer. My big question is, how do you account for the time? And how do you do it in a biblically faithful fashion? You've had many different attempts to do this, day, age, allegory, all sorts of stuff. The standard has to be, is it biblically faithful? And I think I've seen every way to try to do that, and all of them flunked the test. That's why I'm a 6-day recent creationist. Problems with the Bible. The direction of research is atheistic. If the Big Bang so clearly leads you to theism and to God, you would think that some of the major hitters in the theory are theists, or Christian even. But you know, the major players in the field, I can't identify a single theist, let alone a Christian in all of this. The time issue I've already referred to, it's problematic with me. And the order of creation is wrong, as I've indicated. That's usually the problem with all these evolutionary ideas that people put forth. And I like to point out something. Even Christians who like the Big Bang and millions of years, they admit that the end of the universe, like in 2 Peter chapter 3, the new creation, the new heavens and the new earth will be fast. It will happen. The things will be swept away very quickly and replaced very quickly. These are like bookends. You've got the old creation, you've got the new creation yet to come. If one of them is very catastrophic and rapid, why isn't the other one? If God can do it a second time very quickly, why didn't he do it the first time? 2 Peter chapter 3, verse 10 particularly talks about this. And finally, this is very important. When the Big Bang theory is abandoned, what becomes of our apologetic? People want to wed the Big Bang model to our Christian apologetics. But again, the history of science will tell us that every theory we come up with has a shelf life and eventually will pass off the scene. If you make the Bible interpreted in terms of Big Bang, then you have a real problem when that revolution occurs. I may never live to see that, but I'm convinced the Big Bang model, if the world continues, will one day be abandoned. So I urge caution on doing this. Thank you for watching.